Hey, AP Chemisters, this is Mrs. Vandewey bringing you the 10.7 edition of Blank Wall. Folks, we're almost to the end. So this is all about the valence bond theory, hybridization of atomic orbitals. Hybridization is what the electrons kind of do when they are going to bond. Let's just put it that way. And when we talk about 3s and 3p and things like that, and we're bonding electrons between the s and the p's, something happens. That's called hybridization. So what is hybridization? Orbitals in a molecule are not the same as orbitals in the atom. So like we said, s before was like a sphere. All right, so we looked at the S, let's just say S here, and that's a sphere, and P looked like, the peanut, remember that? When we bond with other atoms, these are going to change, okay? And a hybridization, I think of donkeys. Okay, and mules and horses. So if I have a horse, let's say a female horse and a male donkey, they breed, they produce a mule. A mule has the intelligence of the donkey but the strength of the horse. It's somewhere in between. It doesn't look exactly like a donkey, it doesn't look exactly like a horse, it has properties of both. And that's what's going to happen here. We talk about hybridization of s and p orbitals and perhaps even d. So the hybrid for here is a cross between two atomic orbitals. So it says as a general statement, the number of standard atomic orbitals added together always equal the number of hybrid orbitals formed. What does that mean? If I have s's and p's, if I have one s and three p's, I'll end up with 4, and I'll have 4 sp3 hybrid orbitals. It says the total number of orbitals is conserved. Okay. The particular combinations of standard atomic orbitals added together determines the shape and energies of the hybrid formed. And we're going to be talking about this, don't worry. And it says a particular type of hybridization occurs is the one that yields the lowest overall energy. So I've already alluded to sp3 hybridization. And it says it uses one s atomic orbital and 3 p's. So what's going to happen here? Carbon, very, very common, especially in organic chemistry. What's going to happen is that this down arrow is going to be promoted up here. And so now I have half-filled S and half-filled P. And now I have 4 sp3 hybrid orbitals. They're all of equal energy, if you notice. So they're not at the low energy of the 2s, they're at the higher energy of the 2p, they're in between. So carbon has 4 identical hybrid orbitals, okay, and they're called sp3s. So when they talk about the shape of these, notice I have 1 s and 3 peanut-looking ones. Well, I end up with 4 kind of S, kind of P, somewhere in between. I have a big lobe at one end and a little lobe kind of in the middle. And so when I put them all together, I have each of these lobes at the 4 sides of a tetrahedral. So that would also tie in with shapes as well. That the hybridization and the shapes that we learned earlier are all related. They are consistent with one another. So notice sp3, I have 4 orbitals going in the 4 corners of a tetrahedral, of a pyramid, if you will. All right, and so that's what's going to happen with carbon and, say, hydrogen. So if I want to make methane CH4, I now have 4 equal orbitals in which the hydrogen's electrons to come in. And so you'll notice that when I do bond that, here's my sp3. My S's are not turning out real well. There we go. And they will bond then with the sharing of the electrons with these hydrogens that bring in 1 electron. So that shape, as we already learned earlier, is tetrahedral, and the hybridization of an sp3 always starts off as tetrahedral as well. Okay? All right, let's see what else. So it says hybridization geometry now agree. Let's look at sp2 hybridization and double bonds. What's going on here? So let's draw, this is H2CO3, and okay, let's do this. We have C, and we have an O, and we have an H, and we have an H. So what are our rules here? So let's count up all of our electrons. We have 2 for hydrogen and 4 of hydrogen, or excuse me, carbon, and 6 for oxygen's 12 electrons. So 2, 4, 6, 8, 10, 12. All right, those are single electrons. You know what? Let me try that one again. That looks pretty bad. Okay, we're going to try this one more time. Hopefully you know what I was trying to do here. Whoops, come back here. Nope, nope, nope. Sorry about that. So here we go. So CHHO, and then I'll put some dots, there we go, around the oxygen. So now I have my 12 electrons, but what do you notice? A carbon is lacking. So what I need to do is take, let's say, 2 of these electrons and make another bond here. So I have a double bond. So how many bonding sites do I have? I only have 3. I have one with hydrogen, one with the other hydrogen, and 1 site with that oxygen. So I need a total of 3 hybrids, if you will, hybrid orbitals to bond. Okay, so I'm going to hybridize one of these S's, my lower energy, and 2 of my P's. So that gives me 3 sp2 hybrid orbitals. Why sp2? Because I used 1 S and 2 P's, and that gives me 1 unhybridized. The leftover P kind of remains the same. So what's going on with carbon? Okay, so carbon will have, in a sense, you're going to promote this guy to over here, and then I'll have the S and the 2 P's all together become sp2, and then I have the 3rd P all by itself. So the geometry, again, I'm going to take 1 S and those 2 P's, and here are my 3 hybrids. And if you look at this. How can I put these shapes together that they're going to be furthest apart, and it's going to be trigonoplanar? That's what we learned earlier, isn't it? So what happens to this unused P electron? Okay, we're going to make a pi bond out of it. So here is one of my P's, all right, and here's another one of my P. Sorry. Try this again. Here is one of my hybrids. They're going to overlap with another hybrids, and when you have an initial bond, that's your sigma bond. Sigma and single bond kind of go together. The S and sigma and the S and single. It's the direct overlap. All right, but what happens with P bonds? Okay, these P orbitals that aren't being used are going to overlap kind of here and here to create this kind of a shape, and here is some, the electrons in the P. Those P bonds, all right, are going to overlap side by side, and they will restrict the rotation. They just can't go, sliding around here. They will restrict the rotation. They are stuck in that position. And do you recall what happened in Chapter 9 when I had P orbitals, or these P bonds? If I have a double bond, the bond strength gets stronger and the bond length gets shorter, okay? And that's because of this overlapping, bringing these things together, makes them stronger and shorter, okay? Over here, so what does this formaldehyde really look like? Here is your direct first bond. So if I'm doing this, I'll kind of put it in the same way they have it. Okay, so this overlap of the S is, let's say, the first bond between the two. Then I have these sigma bonds here, my single bonds, there and there. And then what? This pi bond is right here. So the second bond of a double bond is the pi bond. Oops, sorry, I should have overlapped it a little bit less than that. So here we go. It's right there. There we go. And so that's what the second bond in the double bond is, your pi bond. So it says in section 9-10, oh, I just said something about that. We learned about double bonds are stronger and shorter than single. Got it. For example, the C double bond or C single bond C has an average of 347, while the double bond has an average of 611. Use the valence bond theory to explain why a double bond is not simply twice as strong as a single bond. So why isn't it, like 700 or something instead of 611? Well, the first bond here is a strong bond. It's your sigma bond. It's your overlapping, if you will, of your hybrid orbitals. So that's your overlap bond, your strongest bond. Not to say the other bond, I'll kind of try to draw it here. There's your P. So this is your sigma. This is your pi. Not to say it is not strong. It is strong, but not as strong as an overlap of the sigma. So you have a strong bond and not quite as strong of a bond adds up to less than 2 strong bonds. That's really what it's saying. Okay, so what about another one? sp hybridization, draw F-ine. Well, F is 2 carbons. Maria eats peanut butter, so M is 1 carbon, F is 2 carbons. So I have 2 carbons put together by a triple bond. Now keep in mind how many bonds does carbon always get? Without an exception, it's 4. So if I have 3 in between here, that means I need only 1 hydrogen on each carbon. So take a look at this carbon right here. How many bonding sites do we have? We have 2. Okay, so that means we only use 1 S and 1 P. 1 S and 1 P for the 2 bonding sites. So I'm going to hybridize those, and that's what these are. And then I have 2 P orbitals that are not being filled. All right, so once again, promote this down electron and put it here, but I'm only going to use 2 of the S and one of the P's to be hybridized, and that's what this is, and then I have 2 P's left over. Okay, so let's see the next one. So the geometry here, keep in mind, I need to have 1 S and 1 P, and this is what I get, and I put them together. It looks like a little bow tie, doesn't it? Okay, so what do you notice about the shape of this? It looks linear to me. And what did we say if we have only 2 bonding sites? It's going to be linear. Okay, there's not much you can do. 2 points determine a line. Well, there you go. So this is what ethene looks like. So I have a sigma bond here, which is a direct overlap, a sigma bond here, which is a direct overlap, and a sigma bond here, which is a direct overlap. So I have 3 of those. And then here is one of my P's, and here is the other one of my P's. They're at 90 degrees of one another, so I have 2 P bonds, or pi bonds, excuse me. Will these rotate? No way, Jose. So if you have single bonds, yes. If you have double or triple bonds, no way. So why do you suppose that the single bond C triple bond requires more energy to break? Because you have 1 sigma and 2 pi's, but not 3 times a single bond. Well, you don't have 3 sigma bonds. You don't have 3 overlaps. You have 1 overlap and 2 of those P's that kind of do the top and bottom thing, which are weaker. So you have 1 strong and 2 less strong bonds together, so you're not going to have this. Now, what happens when we use these d orbitals? Okay, we have a new hybrid orbital, and there's no way I could even think about drawing those, but luckily the book does for me. So look what happens with arsenic pentafluoride. What a great name. So I'm going to use, I need 5 bonding sites. So I go 1, 2, 3, 4, 5. Okay, so I have 5 orbitals, and that's what my hybrid orbitals all shown together will look like. So they kind of look like the little end here and a big one here, but then they're all put together. So there's a little one and a big one, and then a little one and a big one, and that kind of thing. I'm not doing a very good job drawing, but that's what happens. So each of them have a little end and a big end. I want to show you something. Here's arsenic, and I believe that's your 4S and your 4P. I hope that's right. And if I start off here, okay, and how many open electrons do I have for fluorine to jump in with its 7 electrons? I only have 3 open spots, okay? I have an open spot, here, here, and here. I need 5 spots. I only got 3. So what I have said before, I have these D's available. Okay, here's my 3D. Not being used yet. Okay, I'm sorry, not 3D, silly Mrs. Van Noy, 4D, not being used yet, but available. So what can I do to this electron? I can promote it up here. So watch this. I'm going to erase the one I just promoted. How many open spots do I have? Count them, 1, 2, 3, 4, 5. Isn't that what I need? Oops, here? I do need 5. I do need 5 here. And now I have 5 open spots. So what hybridization am I going to use here? I have 1 S, so S. I have 3 P's, and I have 1 D, so it's sp3d. Okay, so that's how the expanded octet works. Okay, so this is what it looks like. So here are my sigmas, which is my direct overlap. So I have 1 sigma, 2, 3, 4, 5. I have no P bonds. I have none of those, up and down things. So I have no P bonds. Will these bonds rotate? Yes. So the fluorine can twirl around. Okay, not a problem. SF6, what's happening here? I'm going to show you something again. Okay, so here's sulfur, 3S, 3P, and here's my unused, haven't been filled in yet, 3D. So here is my my orbital notation for sulfur. How many fluorine spots do I need? I need 6. Right now, I only have these 2 available because, again, fluorine needs only 1 electron, doesn't it? So what do you think I'm going to do? Well, I think I'm going to promote. So I'm going to take this electron and I'm going to promote it to here. Now, how many open spots do I have? I have 4 open spots. But wait a minute, how many do I need? I don't need 4, I need 6. So what do you think I'm going to do next? I'm going to take this electron and I'm going to put it here. Now, how many open spots do I have? 6. Isn't that what I want? I need 6. So what have I used? I have used 1 S, 3 Ps, and 2 Ds. So it's sp3d2 hybridization. And here it is. There's a shape of it, and again, it's octahedral. Okay. Now, what happens to these unused P? Absolutely nothing. They are unhybridized, and they're not part of the thing. And sp3d2 is the most promotion you will ever get. If you have, let's say, a noble gas with all 4 of these things filled, it's not going to promote 4. This is as big as it goes. Okay, so this is how many, or this is what SF6 will look like. So how many sigma bonds do I have? I have 1, 2, 3, 4, 5, 6. So I have 6 direct overlaps. I don't have any of the pi's that goes up and down. I used up all my p's, by the way, didn't I? And so which bonds rotate? Will rotate all the SF bonds. Will rotate all of them because they're all sigma only. Okay, if I had a pi bond someplace, that would not. Okay. So this chart should look familiar, okay? We did this earlier with shapes, okay? And this all ties in. You're going to see this looks familiar. So electron groups is, like before, 2. So electron geometry, the electrons are going to be linear, okay? You don't have a whole lot of choice there. And your hybridization is going to be SP, only SP. And what works here is that if you put like these little, it's supposed to be a 1 here and a 1 here, so isn't just S to the first, and isn't P just P the first? So how many orbitals did I actually end up using? I have 2 total orbitals, right? 1 here, 1 plus 1. 1 plus 1 equals 2. Okay, it makes sense. The hybridization pictures I'm not very good at, so I'll maybe do some of these. All right. Something like that. And there's my linear. So how far away can you get? You have a linear, 180 degrees. So if I have 3 electron groups, okay, the electron geometry is trigonal planar. Okay, and the hybridization we had was sp2. Now again, if I don't put a superscript up there, isn't it a 1? Yes, it is. So what's 1 plus 2? I believe it is 3. So the hybridization picture, I'm really bad at this. All right. And then I'm really bad at this. All right, something like that. So if you look at it, it is trigonal planar. This is linear. Okay. Now keep in mind with the shape, what if one of these were a lone pair? Okay, what if one of those were a lone pair with a shape? All right, you have to go back and look at your picture. What happens? And I would erase one of these, and what shape is that? That would be bent. Okay, so for example, when we talk about, let's say, SO2, okay, we have S, double bond O here, and a lone pair there. That is still bent. Okay, it is still sp2 because I needed to use these orbitals for the lone pair. So I still have, in a sense, 3 sites. Okay, and that will still be trigonal planar, but because they're lone pairs, they don't show up as a shape. That's going to be linear. Let's see here. What about the next one? How about 4? That sounds like a plan. That would be tetrahedral. We saw that earlier. All right, and that's going to be S1P3. Again, you don't need to write down the 1, but I want to show you 1 plus 3 is 4. Okay, and heaven help me, I am no artist, but I'll do what I can. All right, so here's this. All right, I'm really bad. Here's this, and then here's this. Well, there's your tetrahedral, so it kind of looks like this. And so what can occupy these? I can have lone pairs and atoms, okay? So if I have all four of these with atoms, it is truly tetrahedral. What happens if I have a lone pair? Then it's trigonal planar. What if I have two lone pairs? It's bent. What if I have three lone pairs? Then it's linear. Okay, so hopefully you remember going back. But it just is, whoa, what just happened here? There we go. So what happened here, we have, I don't know what's going on here all of a sudden. So I'll just put it back here. The hybridization pictures are still showing us this right here. So they are there. The orbitals are there. If there's a lone pair occupying an orbital, then it won't show up. Okay, 5, the electron geometry is trigonal bipyramidal. I hope I can get this all in here. Trigonal bipyramidal. Okay, I'd like to hear that. 2 times the speed there. And I need to have whole things adding up to 5. So it's S1P3D1 is your hybridization. And I'll just kind of do this. So here is your hybridization orbitals there. And let's think about this. If I have no lone pairs, it's trigonal bipyramidal. Let's kind of review the geometry again. If I have one lone pair, all right, oops, I'm sorry, I erased it from the wrong one, didn't I? Okay, let's try it again. If I have one lone pair, then here it is. That is your seesaw. If I have two lone pairs, I'll put this one back. If I have two lone pairs, it is T-shape. If I have three lone pairs, then it's linear. Okay, so again, this is going back to the geometry. They're all related. All right, let's go ahead and do this next one. So if it's 6, it is octahedral. And that's SP3D2. And again, if you add them all up, you get 6. And I'll draw my octahedral. And I'm only going to erase a couple of these things. So if I have one lone pair, if I have no lone pairs, it's octahedral. If I have no lone pairs, it's square pyramidal. I have two lone pairs, it's square planar. Okay, so that's all you have there. So it says, write the hybridization and the bonding scheme for each of the following. This is how Mrs. van de Walle will do that. Look at your central atom, okay? And so here is bromine. Okay, and how many open spots do I need? I need 3. So let's see, here's bromine. Okay, here's my S, here's my P. I have 7 valence electrons. All right, and what's wrong with, 7. What's wrong with that? I only have 1 open spot. All right, I need to have 3 open spots for the 3 fluorine. So there's my optional D. What happens is D, all right, I'm going to promote one of those electrons into the D thing. So my hybridization is sp3d1, or just D. Okay. How many sigma bonds do I have? I don't have any. If I were to actually draw, hey, let's draw this now. Let me scroll down below so I have a little extra room here. Okay. Let me draw this. So going back to our rules, remember our rules? We have how many total electrons do we have? Well, 7 plus 21 is 28. I have 28 electrons. So here's my bromine. All right, and here is my fluorine, and my fluorine. Okay, so I'm going to put all these in here. See that? How many electrons did I use? I used 24, didn't I? Okay, I have 28 I need to use. Where am I going to put my other 2 sets or 4 electrons? Here. Okay, so how many bonding sites do I have, or how many just sites around the bromine? I have 1, 2, 3, 4, 5. That's why I need to be sp3d. Do I have any double bonds? No, so I have no pi's. How many sigma bonds do I have? I have only 3. 1, 2, 3 sigma bonds. So the geometry is, all right, it is sp3d, so it starts off as trigonal bipyramidal, and I have 2 lone pairs. So erase, erase, and what letter does that look like? It looks like a T to me, so it's T-shaped. Okay, let's try the next one, a little bit different. I've already drawn the structure for you in a sense. I'm observing I do have a double bond. Something that may help this out a little bit is you also have 2 lone pairs around the oxygens, just FYI. So if I were to kind of do this again, I need to put some H's in here because, here we go. Here we go. All right, so what kind of hybridization? Well, I have more than one central atom, don't I? I have a central atom here, and I have a central atom here. And this is kind of typical of the AP. They may give you a larger structure, and you have to tell me the hybridization of each. Well, count. How many bonding sites does number 1 have? I'm looking at 1, 2, 3, 4. Well, what adds up to 4? sp3. How many bonding sites does number 2 have? 1. This counts as 1. So 1, 2, 3. Well, what adds up 3? sp2. 1 plus 2 is 3. So how many total sigma bonds do I have? Let me use another color here. I have 1 sigma bond. The first one of these is sigma, 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 sigma. All of them that I circled in blue are your direct overlap. So it looks like I have 6 of those. All right, how many pi? Well, my second double bond is going to be a pi. I have 1 of those. So let's talk about geometry. Well, if my first carbon I have sp3 with no lone pairs, well, what shape is indicative of sp3, no lone pairs? It's your tetrahedral. Okay, and what about the next one? sp2 with no lone pairs, it's your trigonal planar. Okay. Why don't you draw the next 2? Draw xenon tetrafluoride. Think about how I showed you how you promote into the D block, all right, and then do HCN. Again, you are not going to promote an HCN into a D block because they're the second period elements. Not going to work. But you certainly can with xenon, so pause this and do these 2 for me and then come back. All right, hopefully I paused long enough for you. Let's count our electrons. We have 8 plus 4 times 7 is 28, so I have 36 electrons. So here's xenon, and I have 4. So, all right, I'll do fluorine, 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 and fluorine. All right, and I'm going to put all my dots around here. Oops, there we go. And how many electrons have I used? Well, 8 times 4 is 32. I don't know if you noticed that. And how many do I need to make? 8 plus 28 is 36. So I need to put 4 more electrons in here. So I'll put 1 here and 1 set there. Okay? So my hybridization. Well, I'm sorry, guys. I'm going to have to go here. Here's my S. Here's my P. And here's my D. So as you know, xenon has a full octet, means there's no room for fluorine anywhere. So I am going to have to promote. Let me promote this guy here, and I'll put him here, and then I'm going to have to promote this guy here, and I'm going to put him here. So do I now have enough spots for fluorine? Yes. Okay, so what's my hybridization? sp3, D2. Okay, because I had to promote into the D. Just real quick, can I ever do this? Is this allowed? The answer is no. You will never have sp3d3. Doesn't exist. So what does that tell me? Will xenon hexafluoride exist? No, it will not. All right, can I do this? And what do you think the answer is going to be? No. All right, so will xenon octafluoride exist? No, never. Okay, so the most you can ever promote is to D2. Okay, please know that real quick. All right, how many sigma bonds do I have? Well, okay, let me circle those. I have 1, 2, 3, 4. They're all my singles. I have no double or triple bonds. I have none of these. All right, what's my geometry? Okay, well, let me start off here. Here is my octahedral, and I have 2 lone pairs. 1, 2. What does that look like to you? I'm hoping you're thinking, oh, that looks like square planar, and you are right. Okay, let's try the next one. Are you ready? Sure. Erase this. Let me do this. All right, I may need to erase this. I may need some room. All right, so you ready? Let's do this. HCN. Okay, I have 1 plus 4. Hello. Plus. There we go. Plus 5. That's a total of 10 electrons. Okay, so I have to do this, and I hope you came up with this. This is the only structure there is. There is no resonance structure because hydrogen can only have a maximum of 2 electrons. So you can't make into a double and a double bond. Hydrogen can't have 4. So what's my hybridization? Okay, well, let's check this out. We have carbon with S and P. So when carbon bonds, always promote first. Okay, so how many bonding sites do you have? All right, here's carbon. I have 1, 2. I don't need all these. Okay, I don't need these 2. These are going to be unoccupied. The only ones I need are these. So it's SP. How many sigmas do I have? Let me use a color. Here's 1 sigma and here's 1 sigma. So I have a total of 2. How many pi's do I have? 1 pi. 2 pi's. Sounds pretty good. So I have a total of 2 pi's. Notice that when you add your sigma and your pi's together, it equals the total number of bonds. So what's your geometry? Folks, there's no question about it. SP with 2 bonding sites and no lone pair will always, 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 always be linear. Okay? So what about ethene? Well, let me help you out. Ethene is this. Okay? Take a little time and do ethene. So, and do carbon dioxide while you're at it. All right, hopefully I paused long enough for you to do this. So we're going to look at carbon. Now the hybridization for each carbon will be identical because each carbon is identical. It has 2 hydrogens and 1 carbon attached to each carbon. So if I do the hybridization for one, I'm doing the hybridization for both. So here's my S. And here's my P. Remember, if you start off with carbon, always promote first. Now, how many bonds do I have? I have 1, 2, and then 3. I only need 3 of these things. 1, 2, 3. These are the ones I used in bonding. This P I'm going to reserve for something else. So my hybridization is sp2. Now, does that make sense? If I have 3 bonds, I need 3 orbitals, and 1 plus 2 makes 3. So how many sigmas do I have? I have 1, 2, 3, 4, 5. So I have 5 sigmas and I have 1 pi right here. Adds up to 6. 1, 2, 3, 4, 5, 6. Yes. The geometry, sp2. Okay. What is the furthest away that 3 things can be to one another? And it's going to be trigonal planar. All right, and that is indicative of sp2. If you look on the sheet prior, you'll see trigonal planar. Okay, now ethane actually gets its own shape all for itself. The entire molecule ethane is actually called bow tie. But if you want to look at the geometry of the carbon, it is trigonal planar. What about carbon dioxide? I hope we've discussed this enough that you know carbon dioxide looks like this. Memorize it if you haven't yet. It's what it is. I just want to do my central atom. Okay, here's my S, here's my P. And again, promote always the carbon if carbon is your central atom. How many bonding sites does this carbon have? It only has 2, each oxygen. No lone pairs, just 2 bonds. So I only need these 2. So my hybridization is sp. Okay, so how many sigma bonds do I have? 1, 2. That's what you're using your hybrids for, the direct overlap of your hybrids. How many pi bonds do we have? 1, 2. Hey, how many unused p's do I have? 2. It should make sense. I could go back and say the same thing here. How many unused p's do I have? 1. And I have 1 pi bond. Okay. The geometry. What is sp always? Well, look at the problem above. What is sp always? Linear. And that makes carbon dioxide nonpolar because my dipole moments cancels out. The dipole moments cancel out. It's like a tug of war. Nothing wins. That's why carbon dioxide will not dissolve in water. As soon as you open up your pop can, all the carbonation comes out. That's your carbon dioxide. All right, it looks like you have 2 more. Please pause this, and I'll be right back. All right, hopefully I gave you long enough to do this. So 3 times 7 is 21 plus 1 is 22. I have 22 electrons. So here's my iodine, here's my iodine, here's my iodine. And I'm going to put something around all of these. All right, how many electrons did I use? We'll count them up at 16. I still have 6 more to go, so I put them on my central atom, just like that. Don't forget, if it's an ion, you need to do this. All right, so what's my hybridization? Well, I guess I'm going to go down below. Here's my iodine. How many open spots do I have? I have 1 open spot. How many do I need? I need some more, don't I? All right, so I need to promote. Okay, so if I promote up here, all right, that's sp3. I'm sorry, that's a D1, isn't it? How do I know I needed to promote? Because I needed more open spots, didn't I? Yes, I did. Oh, I'm sorry. Let me start backwards again. Erase what I just did. Okay, let me try this one more time. I forgot about that negative charge, silly Mrs. Vanderwaaij. This is what you do if you have a negative. I didn't show you this earlier. Here's my D. So here's my iodine. That's right. But I do have an extra electron, and I'm going to put it there. Phew. Now this is going to make more sense. So how many open spots do I now have? Remember, I put this this electron fills in that last spot. I have no open spots for the other iodines. So that's what I'm going to promote. Promote this guy. All right. And then what? Let me kind of erase what I had here. I'm going to promote, and I put it here. Okay, so now I have 2 open spots for my 2 iodines. Fantastic. sp3 D1. Okay, and you can leave off the 1 off the D if you want. Okay, does this make sense? I have 2 bonding sites, all right, plus 3 lone pairs. So 2 bonding sites, 3 lone pairs add up to 5. That's what 1 plus 3 plus 1 add up to. So how many pi bonds, how many pi overlaps do I have? I have 1 here and 1 here. So I have 2. How many pi's do I have? None. All right. So my geometry is, well, you tell me. Let's see here. If it's sp3 D2 or D1, I have trigonal bipyramidal to start off with. But how many lone pairs do I have? I have 3. Take 1 away, take 1 away, take 1 away, and it is linear. Okay. Hopefully you can see that. So my shape is linear. Come here. There you go. Okay, finally, last but not least, is ammonia. Hopefully you got something like this. Okay, so here's my nitrogen, here's my S. Remember, I cannot promote. How many open spots do I have for hydrogen? 3. How many do I need? 3. I think it's good. I need sp3. I need all 4 of those. I need those 4 hybrid orbitals for my 1, 2, 3, and don't forget my lone pairs. So how many sigmas do I have? I have 1, 2, 3. How many pi's do I have? None. All right, this is not a double bond, right? It's a single bond I just drew twice. So the geometry starts off as sp3 is always tetrahedral. I have 1 lone pair, so erase it. What does that look like? Trigonal pyramidals. So can I write, well, if I write TP, it could be trigonal planar too. So, oops, trigonal pyramidal. Okay, and there you go. I think that's the end of this section. Here, let me take a quick peek. Boop. Go. Well, this looks like it's the end of the section. Guess what? This is the end of the blank walls. We are done. Let's have some celebration. Woo! All right, so once again, I'm going to leave you with this one last time. Don't wait to be great. Hope it was a great year. Bye-bye.